Very good morning. We continue analysis of variance. One of the important concepts in analysis of variance is decomposition of total sum of squares. We will discuss this today. We will show not only the decomposition but also ANOVA table, and we discuss hypothesis testing, what is basically used in ANOVA. I hope you are enjoying the lecture. Let us see the next.
In ANOVA, it will not go in the same manner like Hotelling T square or your other one, that T test, the way we have developed. In ANOVA, it is a different ball game altogether, because here the primary concern is partitioning the observation. We have seen earlier, I told you that from the population point of view, when I am planning to collect some data, let XIL, this is the observation to be collected from a population where the grand mean is mu and population mean is mu L, then we have partitioned the observation like this. You have seen this one, see left hand side and right hand side both are same. Now, you have collected data, that means you have a fixed value now XIL. So, you have to go by sample grand mean plus your population mean minus again grand mean plus XIL, that value, minus population sample mean, not population, sample mean. So, it is okay. Now, you do little manipulation. XIL minus X bar equal to XL bar minus X bar plus XIL minus XL bar. Square the term. If you square it, XIL minus X bar square equal to XL bar minus X bar square plus 2 into XL bar minus X bar into XIL minus XL bar plus XIL minus XL bar square, fine. You take summation over I, okay. So, I equal to 1 to n. We are assuming that equal size samples are collected from the L populations. So, again I equal to 1 to n, then this side will be I equal to 1 to n, this side will be I equal to 1 to n. Now, what will happen to this middle one? The middle one will become 0, getting me, because of this quantity. So, when you write down sum total I equal to 1 to n sum XIL, this will be n XL bar minus XL bar for n times, that will be also n XL bar. So, this value will become 0. So, your resultant quantity will be I equal to 1 to n XL bar minus X bar square plus I equal to 1 to n XIL minus XL bar square. Okay. Now, see that this one, this is in the left hand side some quantity, right hand side also some quantity, 2 squares is given here. Okay. Achha, this is for a particular population, L population, yes or no? because we have taken XIL, everywhere L is there. But how many L populations are there? Capital L populations are there. So, that means your observation is spreaded over all L populations. So, if I take one more summation, what will happen? What you will do then? You will write down L equal to 1 to capital L, sum total of I equal to 1 to n x I L minus x bar square equal to L equal to 1 to capital L, I equal to 1 to n x L bar minus x bar plus sum total of L equal to 1 to capital L, I equal to 1 to n x I L minus x L bar square. This is also square. Now, in this case, is there any I? X L bar minus x bar, there is no I component. So, that means the same component for n times. So, you can write like this, L equal to 1 to capital L, n will be there, x L bar minus x bar square plus sum total L equal to 1 to capital L, I equal to 1 to n x I L minus x bar square. Okay. So, what will be the left hand side and right hand side? If you see, when we calculate the variance, what we will do? We will subtract the mean value from all the observed values and then square it, and then we divide it by the degrees of freedom. Here we have not divided it into degrees of freedom, but actually what is happening here, this XIL minus x bar, this was the variability is this square. So, for all the observation case, you have subtracted by the grand sample average. So, this quantity is known as sum square total. Okay. You see here that L equal to 1 to L, this I equal to 1 to L, x I L minus x bar square, this is the sum square total, and we have already seen that other one n into L equal to 1 to L x L minus x bar square. This is what is the difference, the variability part from grand mean to the individual population means. That sum you have taken. You see this one, what you have done here, XL bar, this is the population for Lth population sample average, and x bar is the grand sample average, the difference between the two, and then these observations you have squared. So, if there is no difference between the population means, we assume that the sample average also will become same and it will be equal to the grand sample average. So, then this quantity will become 0. So, if there is any variability, this is because of the variability between the population. So, that is why this quantity is known as SSB, and we have seen earlier also XIL minus XL bar, this is nothing but the error part, which is not explained by the which is not explained by SSB. So, this is SSE, sum square error. Now, sum square total is equal to sum square between populations plus sum square error. So, what is happening here then? We are basically dividing the total variability in terms of sum square total equal to variability explained by the population plus variability not explained by the population. correct. So, this is the known as decomposition of decompositioning the total variability into between population variability and error variability. Okay. So, now we have to see the degree of freedom part, degree of freedom. So, when we compute SST, what we require basically? We require x bar. So, there are total n observation and we have sacrificed 1 to calculate our this one x bar. So, degree of freedom for SST is n minus capital N minus 1, where capital N is n into L when you sample from L population and sample size is equal. If sample size is unequal, then this will be your L equal to 1 to capital N NL. Getting me? So, this is for equation for the equal sample size case. This is the equation for computing capital N for the unequal sample size case. Now, come to the between sum square. Now, under in between sum square, how many labels you have? If you see the computation, what you will be finding out? You will be finding out that population 1 to population L, and you will be computing here that bar XL bar. So, here x1 bar, x2 bar like XL bar, and then you find out the x bar. And if you see the computation of SSB, you are finding out that this is nothing but XL bar minus x bar square and then multiplied by n and that summation. So, that means essentially you are using XL bar. So, as there are L populations and there is relationship also with the individual population mean vis-a-vis grand mean. So, 1 degree you are losing here, and as a result you have total L data points and 1 degree is lost by computing x bar grand mean. So, plus n minus L, because this is the rule that the total variability will also be decomposed into the component degrees of freedom. So, total degrees of freedom is n minus 1 and your SSB's degrees of freedom L minus 1, SSE's degrees of freedom n minus L. So, if you make a sum L minus 1 plus n minus L, it is nothing but n minus 1, right hand side n minus L plus L minus 1, sum total will be n minus 1 and which is equal to this. Keep in mind this one.
Can we find out this n minus L from that previous equation?
Which one?
This last, last right from here, can we find out that the degree of freedom from?
Yes, you are finding out. No, what you are using, you are using L populations. So, you have L mean values.
This is okay. This is right hand. The second part.
Second one, what is happening n into L, this is the total observations. So, we are talking about n equal to small n into L, this is the total observation, this side is reflecting the total observation is this, but you have already computed x bar. So,
This is also okay. This portion.
this one,
This portion.
this portion, see how many Excel you have computed
Excel
bar
Excel bar is the
L
number of
population. So, total is n minus L. Okay. So, there is L Excel bar. To compute this one, you require to know all those Excel bars. So, already L degrees of freedom you have lost, you have capital N degrees of observations, L is lost. So, n minus L. So, this is what is the decomposition in the degree of freedom, correct. This total concept whatever we have discussed so far can be seen in a table which is known as ANOVA table. Whenever you go through any textbook on ANOVA or any software you use for ANOVA, what will happen, you will be finding out that one table will be formulated and this table is known as ANOVA table, which is very popular table. Later on even in regression other cases also we will be using ANOVA table. This ANOVA table for the problem we have considered now, there are few items. One is sources of variation, then the sum square what we have calculated SST and SSB, all those things. Degrees of freedom also you have seen, then you have to compute mean square, you have to compute f value, then based on f value you will be accepting or rejecting the null hypothesis. Okay. So, we have considered L population, no other factors we have considered in the present case. So, sources of variation is the different populations, and apart from this you cannot nullify the random effect. So, random effect is coming under error. So, another source of variability is error, and this population and error, these two sources are making the total variability. So, as a result your table looks like this: population, error and total, then SSB, SSE and SST, and you have already seen that what is the degrees of freedom case L minus 1 for SSB, for SSE NL minus L and for SST NL minus 1. This n multiplied by capital L, this is the capital N what I have discussed earlier, that is the capital N. Okay. This capital N, this is n into L, but if you take unequal sample size this is the different one. Okay. Now, what is MSB? MSB is mean squared between populations. This is nothing but sum square between population divided by its degrees of freedom. Okay. Then what will be your MSE? MSE is SSE by its degrees of freedom. So, this MSE will come here. You write like this, MSB is this, MSE here under error, you write under error MSE. So, I am writing again what will happen here: population, then error, then total. These are the sources of variation. Sources, we are computing sum square, that is sum square between populations, sum square error and sum square total. What is our degree of freedom? Degree of freedom, it will be L minus 1, and this will be your n minus L and this will be n minus 1, where n is nothing but capital L into small n. And then we are talking about MS, mean square, which is SSB by n minus L minus 1, and this will be MS SSE by n minus L. So, that means what is this? SSB by L minus 1 is MSB, SSE by n minus L is MSE. Okay. Now, you are finding out a statistics called AF, which is MSB divided by MSE. Why it is F distributed? Ratio of two chi-square variable, because SSB is the square, this is some square and some square, ratio of 2 square, this is F distributed. Okay. And what will be the degrees of numerator and denominator degrees of freedom for F here? Definitely what is there in numerator? SSB by degrees of freedom L minus 1. So, we will be comparing this with L minus 1, and what is the denominator degrees of freedom? N minus L, and you will find out certain value of alpha, and if your computed F, that F computed here is greater than F L minus 1 N minus L into alpha, you will reject the null hypothesis. Okay. So, once you reject null hypothesis, you will accept the alternate hypothesis, that is the issue. The problem. In the same problem, we have done the hypothesis testing, and population, that variability sum square between population is 43.415, arrow SSE is 25.686 and total is 69.101. Degrees of freedom, because there are 3 processes, so 3 minus 1, that is 2, 3 minus 1 is 2, and there are 30 total observations, that minus 1 is 29, and the difference between 29 and 2 is 27, that will be definitely the error degrees of freedom. Then mean square is 43.415 by 2, that is 21.708, and for error, that is again 25.686 by 27, which is 0.951. You see the mean square value is very less. It is so less because there is effect. So, then F is MSE by MSB by MSE. This is 21.708 is MSB and 0.951 is MSE, and that ratio is 22.82, and which is far away from 0, If you see the F table, you will find the probability is almost close to 0. That means, if I say like this is my F distribution, that means you are somewhere here, this one, which is your 22.82. This one is close to 0. So, there is difference. This is what is tested through grossly, tested through ANOVA. First level test is this. There is difference in population, this one, the means, population means, that is what you are testing. Okay.
Any two population, any two means there is a difference between any two population.
No, but here when you test this F test, when you are doing here, your now what is your null hypothesis? Null hypothesis, no differences in population means, correct. What is the alternative hypothesis? At least one pair is different. So, when you complete this one, and if you find that you are rejecting H0, it simply says that there is population difference in terms of population means, but you do not know which pair. So, we have to know which pair are different. Okay. So, next class I will explain this, which pair is different and other things.